Okay, this is lecture 4.4, and we're doing the derivatives of exponential and logarithmic functions today, and away we go. So given this function, find the derivative. So here's my power, not a real nice looking power, but I would just proceed with taking subtracting 1 from my power, the cube root of 4, minus 1. The power comes down, so I need a little more space. Y prime equals cube root of 4 times 5x raised to the cube root of 4 minus 1. Chain rule, derivative of the inside would give me a 5. So I could organize this as y prime equals 5 cube root of 4 times 5x raised to the cube root of 4 minus 1. Not a pretty derivative, but we'll take it. This one is just about reviewing your exponential properties. And if I had e to the pq, I'd have e to the p plus q to bring it into one base. Quotients is using, we can bring it together with one base using subtraction. Base raised to a power, we multiply those powers. Natural log of e to the x. This turns out to be x. We can use the power rule, which brings the x down in front. And we know that the natural log of e is 1, so that turns out to be x. On this one, what would I do here? I could bring the p back up as a power, couldn't I? So I could have e to the natural log, power, natural log of q raised to the p, and e natural log undoes each other, and I get q raised to the p. That one's a little tough. This next one, natural log of p times q, we can expand that using the sum of 2 logs. And the quotient, we can break that into 2 natural logs. Sometimes it's easier to do your natural logs, or to take the derivatives of this expanded version rather than the compact version. So that's why these rules are sitting in here, just as reminders. Sometimes it can be easier done. This is the power rule. The r comes down in front, and we have natural log p. And that definitely is easier to take a derivative with a coefficient. All right, next page. Rewrite using ln, and we got log base 5 of 8. So base 5 of 8, there's a change of base formula that I can use. I can say it's the natural log of 8 over the natural log of 5. It would also be true that I could write this as an log log of 8 over an log log of 5. You could even do this. You could say it's a log base 3 of 8 over a log base 3 of 5. All of these will give us the same value. I think this is the one they were getting at when they said rewrite using ln's. Number 2, can we simplify that into 1 log? Since I see subtraction, that means that it pulls together using a quotient of the 2 arguments. And if I factor just a little bit, difference of squares on top over an x plus 2 means that x plus 2 cancels, and we get an answer of natural log x minus 1. Sometimes it's handy to be able to solve exponential equations where the exponent is the variable. And I could make use of, what I want to do is bring this down to the lower level where we can operate with just an x, not a power of x. So to do that, I'm going to introduce just a log, natural log to both sides. What I do to one side, I can do to the other. No math rules broken. The x can come down. and I get x equals natural log 19 divided by natural log of 3. There's one way of doing it. Now, others may have said, why didn't she do it this way? Why not introduce log base 3? And you're right, you definitely could. Still use the power rule, and I get x coming down. I'd have log base 3 of 3 equals log base 3 of 19. And we know log base 3 of 3 is 1, because 3 to the first equals 3. X equals log base 3 of 19, which is exactly the same as this. This is a change of base formula, so this would have said I have an LOG with a base of 3 and a value of 19. So they do turn out to be the same, just how you want to approach the problem. Number 4, we've got exponential x values, so I'm going to ln both sides, which will allow me to use the power property to bring the variables down, and that will help us get our variables on the lower level where we can work with them. And I want, what do I want? I want to get x by itself. I think I'm going to distribute x natural log 3 plus natural log 3 equals x natural log 2. And I want to get my x terms together, so I had x natural log 3 minus x natural log 2 equals negative natural log 3, just sorting things out. And factor out an x, I'd have natural log 3 minus natural log 2 equals negative natural log 3. It's complicated. And from there, we have x, oops, parenthesis, x equals negative natural log 3 over natural log 3 minus natural log 2. And we could leave it like that. I was just thinking, I suppose we could go, it's natural log of 3 halves and leave it there. Yeah, that's good enough. Lots of playing around. All right, derivative review for e's and logs. Well, we all know that the derivative of e to the x is itself. It is e to the x. If I have e raised to the u, where u is some function, usually some function of x, but it's something a little bit more complicated than just a simple little x. Maybe it's 3x squared plus 7 or something, right? We would have it's e to the u times the chain rule, u prime, so that we can take the derivative of that exponent. A to the u, where the base is not e, we'd have to do a little adjustment. We'd have natural log a times a to the u, because it has that property like e to the x. Its derivative is itself a to the u times u prime. Natural log of x. This is 1 over x. The derivative of natural log u is the chain rule, u prime over u. And log base a of u, well, I can use the change of base formula to rewrite it into natural logs. And then I could say, well, this is 1 over natural log a, because that's just a coefficient, times natural log of u. And if I take the derivative of that, I have the coefficient times u prime over u. So I could call this u prime over natural log a times u. It's kind of nice to see that change of base formula to identify how did we get that 1 over natural log a. And if you can understand where it's coming from, that makes it a little bit easier to memorize. This here is a proof for the derivative of e to the x. And the way to prove that is to stretch back into the beginning of calculus, where we learned what a derivative was. And we use this limit notation as h goes to 0. So if I do that, I would have, let's just kind of follow through, the limit as h goes to 0. I need my function evaluated at x plus h. So e raised to the x plus h minus my function just evaluated at x, e to the x, over h. Okay, good starting point. We know what the answer should be. We should turn out with e to the x, shouldn't we? So the limit as h goes to 0, e to the x plus h can be written as e to the x times e to the h using properties of exponents. And then we notice that we have an e to the x in common. So let's do a GCF. Oops, blue. The limit as h goes to infinity or into 0, factor out e to the x, that leaves me e to the h minus 1 over h. I can bring out this because h is going to 0, x is unaffected, so I could bring by the product property of limits, I could bring that out front and be sitting with the term that does involve h here. And now the dilemma, this is the difficult part of this proof, is knowing that this particular limit does go to 1. And that's a bit of a stretch for us in Calc 2. So I get e to the x times 1, which gives us e to the x. If you look in the textbook, under this section, what are we, 4, you will see them talk about this particular limit, and they just established that it does go to 1. They provide a table proof, and they provide a graphing, a picture to show that indeed as I head to 0, this limit does go to 1. Now those are not, conclusive evidence that it is 1, but it is convincing enough. It's a little bit harder to show why that limit goes to 1. We need to look in a little more advanced calculus for that. All right, on the back side, we actually get into some practice of taking derivatives of e's and other bases. So I'm identifying my u right here, and I know the pattern goes e to the u times u prime for this derivative. So I'm going to have e to the 6x to the 4th because the derivative of e is itself, and then I need to take the derivative of the exponent, and it looks like that's going to turn out to be 24x cubed times e to the 6x raised to the 4th. For b, I think my first step would be to rewrite this as a 1/2 power. Okay, so my whole u is right there, and I need the derivative of e is e to the u, so it will look like the original. And then I've got to chain off, and now I need the derivative of just, let me highlight it, of this. That's not too bad to take. The derivative of that 1/2 comes down. I get the polynomial raised to the negative 1/2. Oh, then we got to step inside. Don't forget the extra chain rule here. Step inside, and we'd have 6x plus 2. All right. There's probably some cleaning up to do here. So let's do a little sorting. Cleaning the house. E to the square root stuff. 3x squared plus 2x plus 4 over, I see that negative square root, so I'm going to go 3x squared plus 2x plus 4. I have a 2 on the bottom, and with this I see I can factor a 2 out. I'd have 3x plus 1. So I'm going to let those 2's cancel. headset keeps falling off. Okay, the 2's are canceling, and it leaves me, where am I going to write this? 3x plus 1 as part of the numerator. That one I think is an easy one to miss one of the chain rules. C. 3 raised to the cotan of x. All right, this is like a y equals a to the u, and I know the pattern for that. It is natural log a times a to the u times u prime. You just need to have that working knowledge of all your derivatives, and then life is a box of cherries. My a is the 3, so I'm going to have natural log of 3 times itself, so 3 raised to the cotan of x, and then I need to take the derivative of my exponent. The derivative of cotan is a negative. I'm going to go put that negative way out front, and the derivative is a cosecant squared x. The derivative of the inside x is 1. And I think we've got it. And we laid it out pretty nice. I don't see any reason to rewrite that. It's sitting in a very nice order. Whew. D. Take a look first. Do you always scan your problems? I do, just to see what is coming up. I've got a chain rule here. Here's like u to a power. Okay, I can deal with that. I know power rule. And then I've got a base. This is like an a to the u type scenario. Oh, I don't think this will be that bad. Hey, hit pause and try it yourself, you guys. See if you can get it. Does that make sense for the power of 10 term? 10 comes down, goes to a 9. Leave the inside alone. We got an x squared plus 2 inside. Now, step inside, take the derivative of that, and you get a 2x. Add on. I need to know the derivative of that. We talked about it just a bit ago. Natural log a to the u times u prime. So I would have natural log 10 times 10 raised to the x squared plus 2. And the derivative of the exponent is a 2x. What could you do? The only thing in common is 2x, isn't it? You could factor that, I suppose, way out front. It doesn't gain us a whole lot. It really does not simplify this a great deal. So why am I writing it? I don't know, just because. We need a natural log of 10, and then that's going to get multiplied by 10, x squared plus 2. I guess I just like to always practice simplifying the best I can, and I'm looking at my mismatch of parentheses and clearing that up. I left one hanging there. Yeah, I don't know. It's not tremendously better, but it is factored form. And E, oh, we got a little product rule going on. So I'm going to say y prime, yep, I'm introducing a y on this side. Y equals x cubed times e to the 2x. So product rule. Try it on your own, then check back in and see if we agree. So what did I do there? Derivative of x cubed became 3x squared multiplied by the second. I'm thinking f and g, right? F prime g plus g prime. This is my g prime, isn't it? And I had e to the 2x times 2 from chain rule, and then times the x cubed. What could we do? There's a lot actually in common. We could pull out an x squared e to the 2x, leaving us a 3 plus an x times the 2. How about a 2x? And then swipe, distribute back in your head to double check, make sure that we are even Steven, and we are. Product of those items. All right, natural logs. Natural logs. What is the formula for natural log of u, and the formula meaning the derivative formula? So u prime over u. That's where we're headed. This is our u. So y prime is going to be 6x over 3x squared. Oh, we gotta, without a doubt, reduce, don't we? 6 divided by 3 is a 2. X over x squared is an x. Log log, that has a base of 10. There is a formula for log. Log of u, the derivative of that is a 1 over natural log of the base times u prime over u. Okay, just gotta know them, don't ya? Y prime equals 1 over natural log of 10 times the derivative of my u would be 2 over a 2x plus 3. And I could leave it in that format, but I also could bring it all the way back together. I don't know which looks better, which front and back, it doesn't really matter. Just use some parentheses to make it clear that it's just natural log of 10. On G, we have a base of 3. We have e to the 5x. Oh, goodness. What do I want to do? We can deal with this. So here's my base, which is like the a, isn't it? This is a, which is base. And then I have e to the u, and we know e to the u is e to the u times u prime. But this all is my u, so that's a u prime over u. Okay, I think I'm going to go this way, 1 over natural log of the base times u prime over u. That is my game plan. So did a scan, kind of developed a feel for the problem, and then try to decide what makes the most sense for me to do. And I'm going to get a 1 over natural log of 3, because our base was 3, times a u prime, e to the 5x. I'm just going to indicate that I need to take its derivative over itself, e to the 5x. Now, this looks like it's going to simplify really, really well. I still need to take the derivative of this, so it's going to be a 5 e to the 5x over e to the 5x. Because I needed that derivative, and its derivative looks like that. Now, 5x, e to the 5x over e to the 5x cancels. I get 5 over natural log of 3. There is a different way to do that one, and I think I'm going to go ahead and do it. Because when I started this problem, I almost thought about doing it this way, where I brought the power down, log base 3 of e. And log base 3 of e is really just a, what do I want to say? Log base 3 of e is a number. So really, that is like a coefficient times my 5x, which really makes a nice, easy derivative. I have this log base 3 of e. The derivative of 5 is simply 5. And now you're probably asking me, well, wait a minute. That doesn't look like your answer on the left in the blue, but it is. Because I can use a change of base formula to get into natural logs. And change of base formula says it is the top number over the natural log of the base, and then I need to multiply by 5. And natural log of e is simply 1. So, woohoo! We have a match, except that says prime. Yeah, so there's a couple different approaches on those. All right, our final topic. We did not do these last year, but there is a thing called logarithmic differentiation. Sometimes the properties of logs can be used to simplify the differentiation process. Even if logarithms themselves must be introduced into the step of the process, it can make it easier. So, this is called logarithmic differentiation. And sometimes it is clearly the case that I have to do it because I've got my variable sitting in the exponent, which kind of stinks. Variable in the exponent. So how do you deal with that? Well, when we solve equations, remember how we started the day, I don't know, something like that, and we introduced a log to both sides so we could get that x to come down? That's kind of the way we're going to start here. So I'm going to introduce a natural log to both sides, and that will allow cosine x to swing down into the normal level of the equation. Now, if we take the derivative with respect to x, so differentiate, a long word, differentiate with respect to x. Got that? The WRT is with respect to. Kind of common in math to write it that way. All right, the derivative on this left side, I would have 1 over y dy dx. Right? U prime over u is our pattern for natural log, and y was our u. On the other side, we're into a product rule. Derivative of cosine is negative sine x times natural log x. Added with derivative of natural log x is 1 over x times cosine x. And lordy lordy. All right, we can get to dy dx by multiplying up by y. And I'm going to use a bracket one. Negative sine of x, natural log x, plus cosine x over x. Love it. If my equation or my derivative needed to be in terms of x, then what will I do? I will substitute for this. Substitute. And my final answer then, here's the derivative, dy dx is equal to, well, y is equal to x raised to the cosine of x, and then everything else stays the same. Negative sine x, natural log x, plus cosine x over x. And there's our derivative. It's kind of a clever technique. Works when you have variables up in the exponents. That is a long lesson. I hope it went well for you. Watch it again or go to those parts that were a little bit tricky for you. Beautiful. Have a good day.